What if I told you that one of the biggest reasons Earth looks the way it does today is because the ground beneath our feet is constantly on the move? Not fast enough to feel day to day, but over millions of years, continents drift, collide, break apart, and crash back together like slow-motion puzzle pieces. It's plate tectonics, and it's the reason we have mountains, oceans, earthquakes, volcanoes, and even the continents themselves. But now think about this. What if it all just stopped? What if Earth's continental plates suddenly froze in place? You probably don't think much about tectonic plates in your everyday life, but you should. They shape the land you live on, the climate around you, and even life itself. If Earth's plates were to freeze if they stopped moving completely, it wouldn't just be a minor geological hiccup. It would change almost everything we take for granted about how our planet works, and not in a good way. Let's start with what tectonic plates actually do. Earth's crust is split into massive sections, called plates, that float on the softer, semi-fluid upper mantle beneath them. These plates are always shifting, sometimes sliding past each other, sometimes diving beneath one another, and sometimes pulling apart. Their movements create earthquakes, drive volcanic eruptions, and form the tallest mountains on Earth. But they also recycle the Earth's surface and regulate the planet's temperature and atmosphere over time. Without movement, we lose all of that. So, what happens if those movements suddenly stop? No more earthquakes might sound like a relief, but it's not that simple. Earthquakes are a symptom of a living, breathing planet. They're signs that energy is being released, pressure is being balanced, and the crust is staying dynamic. When that stops, it's like shutting down your circulatory system. It might feel calm at first, but it's deadly in the long run. Volcanoes would go quiet too. Again, that might seem like a good thing on the surface. No eruptions, no ash clouds, no lava destroying towns. But volcanoes are crucial for releasing heat from Earth's interior and venting gases like carbon dioxide and water vapor. Without volcanic activity, the deep Earth would overheat, pressure would build with nowhere to go, and long-term cooling of the surface atmosphere could throw global climate systems into chaos. You'd also lose mountain building. The Himalayas, for example, formed because the Indian plate is colliding with the Eurasian plate. If those plates froze, the uplifting would stop. Over millions of years, wind and rain would wear down Earth's great mountain ranges without new ones forming. That's not just a problem for climbers and geologists, it affects how rivers flow, where people live, and even how weather patterns move across continents. But even deeper than the surface level effects, plate tectonics is part of Earth's internal engine. It keeps the carbon cycle going, which helps balance temperatures and the atmosphere. Tectonic plates drag carbon deep into the Earth when one plate sinks under another, and volcanoes return some of it to the surface. This back and forth process is one of the reasons Earth has stayed habitable for billions of years. Stop the plates, and you stall this natural thermostat. Over time, carbon would build up or disappear from the atmosphere in ways that could tip Earth toward a runaway greenhouse effect, or plunge us into an ice age. But to really understand what's been lost when tectonic plates stop moving, you've got to know how much they actually do for the planet. These massive plates, drifting at speeds you could compare to how fast your fingernails grow, or your hair in some places, are what keep the engine of Earth running. Think of Earth's outer shell like a cracked eggshell floating on hot, gooey custard underneath. That outer shell is the lithosphere, and it's made up of the crust and the uppermost mantle. It's split into a bunch of big plates like the Pacific Plate, Eurasian Plate, Nazca Plate, African Plate, and several others, all gliding over a more flexible layer called the asthenosphere. The asthenosphere is where the heat from Earth's interior rises and causes a slow churning motion convection currents. That's the real driver here. At places like the Mid-Atlantic Ridge, new crust is being created. At subduction zones like off the coast of Japan or South America, old oceanic crust sinks back down into the mantle. It's like a conveyor belt. One part creates new Earth, The other recycles the old. That balance is why Earth's surface doesn't balloon out of control or collapse in on itself. You've got three major types of boundaries where all the action happens. At divergent boundaries, plates pull apart and make room for new ocean floor. That's where we get underwater volcanoes and new crust forming. At convergent boundaries, they smash into each other and one gets shoved down. This causes trenches, quakes, volcanoes, and entire mountain ranges like the Andes or the Himalayas. Then you've got transform boundaries, where plates grind past each other sideways, like at the San Andreas Fault in California. That one alone is responsible for some of the biggest earthquakes in the US. So when all of this stops, you're not just freezing plates, you're shutting down Earth's biggest life support machine. This is the most interesting part. Plate tectonics drives the formation and breakup of continents. Supercontinents have come and gone throughout Earth's history. One of the earliest known was Columbia, or Nuna, formed around 2 billion years ago and broken up about 1.5 billion years ago. Then came Rodinia, about 1 billion years ago, which later split into several landmasses that came together again to form Pangaea. That supercontinent eventually broke into Laurasia and Gondwana, and those fragments became the continents we know today. All of that movement helped shape evolution itself. As continents shifted, climates changed, oceans opened and closed, and species were forced to adapt, migrate, or go extinct. Freezing plate motion would lock Earth into a single configuration. Over millions of years, that static setup would rob ecosystems of the diversity that comes from environmental change. Right now, we can track plate movements in real time using satellite data and ground-based instruments. That's how we know that the Pacific Plate is moving northwest at about the same rate your fingernails grow. It's how we understand why the Himalayas are still rising, or why California experiences so many earthquakes along the San Andreas Fault. We also know that plate motion hasn't always looked the same. In Earth's early days, things were hotter. During the Archean period, between 4 and 2.5 billion years ago, Earth's mantle was up to 250 degrees Celsius warmer than it is now. Some scientists believe that back then, plate tectonics didn't work the way it does today. The crust may have been stuck in a stagnant lid, regime no subduction, no spreading ridges. Others argue that subduction zones started appearing around 3.8 billion years ago, but they were small and temporary. It's likely that modern-style plate tectonics started sometime between 2.2 billion and 800 million years ago, depending on who you ask. The emergence of certain rock types like blueskist, which only forms in cold subduction zones, suggests that by 800 million years ago, plates were definitely moving in the way we recognize today. Some even suggest that tectonic activity goes back further, all the way to the Hadean Eon, over 4 billion years ago. Understanding all this has taken decades of careful detective work. Plate reconstruction techniques are incredibly detailed. Scientists piece together the positions of past continents using clues like magnetic stripe patterns on the ocean floor. Those tell us how plates have moved since the Jurassic period. Hotspot tracks like the Hawaiian island chain give absolute directions for where plates have drifted since the Cretaceous. And when data is sparse, researchers use paleomagnetic poles and apparent polar wanderpaths to chart how plates have rotated and shifted across time. Other clues come from the fossil record, ancient sedimentary rocks, and the locations of ancient mountain belts. For example, matching fossils found on the coasts of Africa and South America prove those continents were once joined. Matching geological features like ophiolites, chunks of oceanic crust found on land show us where long-lost oceans once existed between ancient plates. All of this paints a picture of Earth as a dynamic system that's constantly reshaping itself. But over the last few years, new studies have added even more detail. Researchers now believe that instead of just a handful of massive plates, Earth's crust is also made up of over 1,200 smaller pieces, called terranes. These terranes include fragments of oceanic crust, continental crust, and mobile zones like mountain belts. They've formed, shifted, and collided over billions of years, breaking apart and rejoining in countless different patterns. This more detailed model helps us understand how Earth's crust has evolved on both large and small scales. So, if all this motion came to a sudden stop, you're not just talking about a frozen crust, you're talking about locking up the entire geological, atmospheric, and biological engine of our planet. It would be a slow unraveling. Erosion would grind down mountains, but nothing would rise to replace them. Volcanoes would stop releasing carbon, but weathering would continue sucking it out of the air. Eventually, Earth's climate could spiral into extremes, either too hot or too cold to support complex life. The oceans, which are reshaped by plate movement and seafloor spreading, would stop changing. Sea level dynamics would shift. Ocean currents, which are partially driven by the shape and location of continents, could become less stable. The whole interconnected system that keeps Earth alive and changing would begin to decay. It's not just that things would be quieter. Life as we know it relies on change. Evolution thrives on disruption, adaptation, and movement. Freezing plate tectonics would strip the world of its long-term variability. Without the cycle of continental breakup and reunion, without the shifting boundaries that define our continents and oceans, Earth would become geologically silent and ecologically stagnant. The scary part? We wouldn't notice much right away. A generation might go by, maybe even several, without realizing what had been lost. But over millions of years, the consequences would become obvious. Mountains gone, volcanoes silent, climates locked in place until the atmosphere shifts uncontrollably. And with that, ecosystems would collapse, oceans would stagnate, and the planet's ability to recover from natural or even human-caused damage would shrink. So the next time someone says, "The ground beneath your feet is solid," you'll know better. It's not solid, it's alive. And that's a good thing. A moving planet is a healthy planet. Plate tectonics might feel distant and abstract, but it touches every part of our lives, from the air we breathe to the shape of our coastlines. And now that you know what could happen if those plates suddenly froze, doesn't it make you wonder just how much of Earth's balance depends on things we never even see? What else are we overlooking that's quietly keeping our world in motion?